Okay, people, 4.3 is what derivatives tell us about graphs. 4.4 is L'Hopital's and indeterminate forms. And 4.5 is putting it all together and sketching curves. What questions do you have? Yes, Fiona.
Can you go over how to draw the graph? Yeah, and then no, it's 60 gas and 48 gas.
So in which section? Because I think I've 4.3. So now we're looking at finding the actual curve based on the information we've got, right? So you said 48. Do you want to do 47 or 49? Okay. 47. One half x to the fourth minus 4x squared plus 3. So it asks me to find the intervals of increase and decrease, extremes, inflection points, and intervals of concavity. And then it says, put all that together and draw me a picture, right? So I got to go through this whole spiel. And I know to get my intervals of increase and decrease, I need my critical numbers. So I need the first derivative. To get my intervals of concavity, concave up, concave down, I need the second derivative. So I might as well start right there. What's the first derivative of this equation? And then my second derivative. Great. So A and B, dealing with increase, decrease, maximum, minimum, those things all deal with the first derivative. So let's start there. In order to know where my function is increasing and decreasing, I need to know what about the derivative. That's going to give me the critical numbers. But to know where I'm increasing and decreasing, I need to know where my derivative is positive, negative. And that means I need to know where it's zero first. So you're absolutely right. I start by saying, where is this zero or undefined? But this is a polynomial. It's defined everywhere. I need to note why I'm ignoring that option. You can't just only worry about zero. I need to make sure I know, oh, where's this undefined? It's never undefined. Where's that zero? I take out a 2x, and I'm left with, which I can factor further. So I have three critical numbers where we're equal to 0. I have x equals 0. I have x equals positive 2. of x equals -2. Now I make a sign chart. Put these on a number line, find out what's going on in between those values. Your choice on how to assemble this sign chart. You can either do each factor separately, or you can just go directly into the whole first derivative. I'm going to do each factor separately. I think that's easier. So I make a line for each one. And I multiply these together to get y prime. So I need to plug in numbers that are in these regions and multiply the signs. A number less than -2. A number between -2 and 0. Good catch. Between 0 and 2, I can use 1, and bigger than 2, I can use +3. Now I just plug in to 2x. Doubling a number keeps its sign. If I subtract 2, the only one that's positive is 3 minus 2. If I add 2, the only one that's negative is -3, because the rest of these give me a result that's positive. I multiply these pieces to get y prime, so I multiply these signs. Negative times negative times negative. 2 negatives make a positive, multiplied by another positive. 2 positives times 1 negative, and 3 positives. So right now, I think this graph goes down, up, which means we are decreasing on these two sections. Everything less than -2 and everything between 0 and 2. If I'm in here, I'm decreasing, or if I'm in here, I'm decreasing. And I'm increasing here or here. That's all the first part asked me for. Where are we increasing? Where are we decreasing? Second part says, what are the extremes? But I can get that right from this chart, can't I? Down then up, I must have, aha. Up then down, I must have a maximum. Down then up, I must have another minimum. But it asks for the values, right? It asks for the maximum and minimum values. Those are the y values. So I need to take those numbers, plug them back into the original equation. If I put in -2, a half times 16 is 8. 4 times 4 is 16. 8 minus 16 is -8. Add 3, I get -5. Put in 0. 0 minus 0 plus 3. And when I put in 2, it turns out to give me the exact same value as when I put in -2. So my minimum value is -5, and my maximum value is 3. Local. I should say local on all of these. So far, so good. So now I have a W, and I have 3 points on that W. Down, up, down, up. Part C asked me for inflection points, and intervals of concavity. Okay. This needs the second derivative, which I already wrote down. Scroll way back up here. There. What does it mean to be an inflection point?
So when the concavity changes.
Exactly. Which means I need to know where we're concave, which way, and I need to know where we change. Now, I could change at a physical point. I could change if there were any places where this thing was undefined, just like with our critical numbers. In order to figure out what the possible inflection points are, I need either set this equal to 0 or figure out where it doesn't exist. Same spiel about doesn't exist as before. I don't have to worry about that part. Polynomial.
Do you test assessment, you have to write it out with the D and E or what?
I would absolutely want to see that. Especially if there's a case where, I'm asking you, this is a polynomial, I got lucky. But if I look at problems like come back here. Like number 10 here. That's a quotient. I've got two places that it's undefined. I know right away those are going to carry through to F prime and F double prime as well. So I will have places where that's undefined. But if you can tell me at the very beginning, hey, this is a polynomial, it's never undefined, then you can carry that all the way through. So as long as you say it once, you're covered. Potential inflection points are where we change from up to down, means I need to know where it's 0. Ew. Well, that's a gross number. Grab me a decimal approximation, at least 2 decimal places. What is this number? You own calculators. What is the square root of 4/3? $1.15. Good enough. Because I'm going to make a number line again. And on that number line, I need to know which side of it I'm going to be on. So I've got negative root 4/3 and root 4/3. And I need a number that's smaller, a number between, and a number that's bigger. If I don't at least know roughly what this number is, I can't know what number is bigger, right? So I know this number is 1.15. I can use 2 here. I know this negative positive, I use 0 there. And I use -2 here. I didn't pick those randomly. Those are the same numbers we had for our critical numbers in the previous part. That's helpful. It's not required. I need to plug into y double prime. Since that did not factor, I can't do a separate line for each one. I'm just going to plug in. -2 squared is 4. 4 times 6 is 24. 24 minus 8 is 16. There's my stupid little smiley face. If I'm positive, I'm concave up. 2 squared is 4. Hey, this is going to give me the same answer. 24 minus 8 is 16. When I put in 0, I get 0 minus 8. That's negative. We're concave down. My concavity does change. It changes at that point. But in order to get the y values, because it asked for the points, I need the y values. I have to plug that back in here. 1/2 root 4/3 to the 4th minus 4 times root 4/3 squared plus 3. Yes? But when you square a square root, what happens? Okay, so that's just 4/3. I square a square root, but I'm looking at a 4th power now. That's squaring twice, isn't it? Because 4 is 2 times 2. So I can think of this as 4/3 squared. That makes my life a little easier. 4 squared is 16. Half of 16 is 8 over 9, because 3 squared. 16 over 3 plus 3. Common denominator is going to be 9. This is a negative number. 8 minus 48 is negative 40, plus 27 is negative 13 over 3. If you took this decimal and plugged it in, you'd get negative 4.3 repeating. You could use that as well. These are even powers, right? When I put in the negative value and I square it, it's going to become positive. When I square it again, it's going to become positive. I'm going to get the same value. Now, how do I draw the picture? Because that's really the question you asked me. I did all of this so I could do this step. Here's what I know so far. I have 5 points. I have the 3 extremes, right? 2, -5. -2, -5. 0, 3. And then 4/3, which is a little bit bigger than 1, -4.3. 1, 2, 3, 4.3. There. Same thing on the other side, right? So we're going to be concave down until we get to here. We're going to turn and be concave up. So I know from here to here, we're going this way. Oh, wait a second. That's wrong. Where's my mistake?
Supposed to be -13.
27 over 9. So that's going to be 13 over 9. 13 over 9 is a lot bigger than 13 over 3 in terms of this. So I get negative 13 over 9, 1.444. That's up here. And then we turn and we're concave down. And then we're concave up. That's all I can draw. That's the picture I can give you at this point. I do know that this is going to keep going this way. And this is going to keep going this way because we were decreasing, increasing, decreasing, increasing. The piece I didn't get in this section that I would get in section 5 is the intercepts. That would be able to be found here, but I don't know what they are. I didn't solve them. You got it. Literally, it's the smile and the frown. And I can do half of it on either side, still be concave down or concave up. A cup and in the typesetting program I use to write all this stuff, that's actually the symbol for that, the cup. And then it's inverse, the frown. You'll notice this was not short. Better? It does say you should use a graphing device to check this. So y equals 0.5x to the fourth minus 4x squared plus 3. And I know this graph doesn't really have a lot going on way out when x is really big. So I'm really only looking at numbers around -2, -3, -4. I'm going to change my x window to go from -4 to 4. And hopefully I get a picture that kind of resembles the one we drew. Not bad at all. And yeah, the x-intercepts are between -2, -3, -1 and 0, 0 and 1, 2 and 3. Yeah, I'm okay with that. More questions?
Of
course. Hmm. The other pieces that show up in section 5 include discussions of things like symmetry, right? And I noticed that this graph is the same on the left as it is on the right. We didn't talk about the symmetry here, but if I go back and I look at the original problem, the original equation, x to the fourth, x squared, what power of x is on this? There's no x's there at all. Makes it an x to the 0th. 0, 2, and 4 are all even numbers. This is an even function. It's the same on the left as it is on the right. That is another way I can help myself with doing these calculations and knowing that I'm going to get the same y value both times. And if I'm going to correct it, I should correct it everywhere. So I really only did need to check what happened when I plugged in a positive number. Because I'm going to get the same thing when I plug in a negative number. Yes.
So let's say one of them were odd.
Then it would actually turn out to be neither. If I have a mixture of even powers and odd powers, I don't have symmetry. It'd be neither. Not odd, not even. The easiest way to check is to put a minus sign in with all of the x's in the problem. So let's consider this equation. Which I just now made up out of whole cloth. If I want to know if this is even or odd, what I do is I plug in a minus x. And I ask myself, what happens when I simplify the minus signs? Take a negative, raise it to a third power, what happens? Negative times negative times negative. The result is negative. Take a negative, square it. Five times minus x is the same as minus 5x plus 1. The rest of this is comparison. I want you to compare this to this. Are the signs exactly the same? If this is not true, it is not even. So they're not exactly the same, we're not even. Are they all opposite? I've got a minus here and a minus here, those are opposite. But I've got a minus here and a minus here, those are not opposite, right? So this is not odd because it doesn't match this either. And if we actually graph this function, which I made up, so I have no idea what the picture looks like. That's not the same on the left as it is on the right. So it's not even. And if I turn it upside down, does it look exactly the same? No. Because right now it goes through the top half above 0. And if I flip it, it isn't the same. So what's down here is not the same as what's up here, and what's down here is not the same as what's up here. It's not odd. Does that make sense, Simon? Wonderful. More questions? By the way, it turns out in the long run that being able to keep track of powers is exactly what you need to figure odd and even, except that there are other functions like trig functions that have odd and even, and that means there's got to be a way to relate those things to powers of x. Later. Yes, I know.
Can you go over, in section 4.46, it has it, and not.
So A and B are just numbers. We just don't know what numbers they are. So let me think about what could happen. As x gets bigger and bigger and bigger, what's going to happen to that number? A is a constant. The whole number gets smaller because this bottom is getting bigger, but the top is fixed. At the very worst, that's going to be 0. But in the limit, it will be 0, right? As x goes off to infinity, what happens to that number? Either it gets huge and positive, or it gets huge and negative, depending on the value of b, right? Or, the very worst, b might be 0, in which case I get a 0 up there. So this is going to go to 1 plus 0, either to the positive infinity or negative infinity, right? In either case, that's an indeterminate form. And that's why I need my L'Hopital's rule game. Because this is an indeterminate power. And the problem is that L'Hopital's rule only works for indeterminates that are division, right? So I have to do some algebra to mess with this sucker. And to get stuff out of powers, what do I do to get stuff out of powers? But I don't know what the root would be because the powers have got a variable in it, right? There was another way to do that. And it's similar to what we did when we took derivatives. Again, but I don't know what the root is. If I knew what the power was, I could flip that. This power's got a variable in it. This is the example I did not do at the end of class because I was running low on time. If we go back and look on page 315 at example 9, I have this 1 to the infinity garbage again. And I put an ln in there. And if I put an ln in there, what can I do with that power? I can bring it out front. Now, again, I think about what's going to happen as we go to infinity. This piece is going to be infinity. And this piece is going to be ln of 1. This is infinity times 0, which is still indeterminate. And now I know how to mess with that because I did those examples. If I have multiplication, I need to switch them to derivatives, to division somehow, so I can use L'Hopital's rule. There's a bunch of funky algebra that happens between here and the end of this problem. But I'm just going to treat A and B like they were numbers. By the way, if that bothers you treating A and B like numbers, replace them with numbers. Put in 2 and 7 and go to town. Just keep track of where you use the 2 and where you use the 7, then go back and erase the 2s and 7s and put in the A's and the B's. You're still looking at me like I'm a space alien.
So we just like solve it based on.
My goal is to get further down doing some more algebra to get either 0 over 0 or infinity over infinity. There's a little bit more algebra that needs to happen between here and there. Because what I've got right now is a product. If I've got a product, I can switch it to become division. Then I can use L'Hopital's rule. My buddy L'Hopital. More questions, ask me more things. Well, I am happy to think about all of this stuff in the abstract. And to simply use this for purposes of just doing math for the sake of doing math, that's kind of dumb. This is not sit around and do math because math is cool. Although that's one of my favorite things to do. I'm a geek and a weirdo. I understand that. I want to put this in practical terms. What do I use this sheet for? And the ideas behind all of this are to take the problems we've just done for random functions and apply them to real world functions. I am going to have to run power to the new field house. Yes? Those power lines have to go somewhere. It's going to cost me a certain amount to build a hanging power line that runs down to the side of the building and then gets power into the building. It's going to cost me a different amount to dig a trench and put the power line underground. Where should I put the power line? Where's it coming from? Where's it going to? Quite often, the correct answer is to do some combination of both. To run the power line above ground to a certain point, and then to put it under the ground. Like if I've got to go under a field y'all want to use, I don't want to put a power line hanging over the middle of it. I might actually need to put a post in the middle of the field. That'd be a bad thing to try and play football around, wouldn't it? Where's the balance? Where do I do which part? How do I take this so that it doesn't cost me more than it could? I just came up with a calculus idea. I want to find a cost and I want to minimize it. My goal in doing all of this crap is to now say, let's take these ideas of finding maximums and minimums and inflection points and put them to use in terms of practical situations. So if I think about the idea, if I can come up with some cost function, and I can find a minimum on that, maybe this is the number of feet of wire that is above ground, or the number of feet that's below ground, but somehow I can turn this into a problem about the number of feet, and then I say, well, this is where I put the change from above ground to below ground to save me the money. Maybe I'm going to spend money on advertising. Most advertising returns, when you start advertising, you get a pretty big return. And then everybody's seen your ad. And after a while, they get tired of your ad. But the more you spend, the more you'll bring in, right? At some point, each additional dollar spent brings in less than it did before. That's not a maximum or a minimum. That's a change in concatenating. Finding maximums and minimums and inflection points isn't about drawing pictures. It's about return on investment. It's about not losing my shirt spending on money I don't have to. It's about all these rigged problems that I'm going to set up and then say, what's the best option? That's what we'll do tomorrow. We'll go through the process of making sure we can set up the problem, and these problems will be ridiculously rigged to start with, because I want the math not to be insanely difficult. But I can take this exact idea, go over to the chem lab, go over to the finance department here at school, and figure out what to do in the real world, as long as I have the idea in my back. I will see you all tomorrow. Have a wonderful rest of your day.